Hello? Can you hear me?
Yes, you
Okay.
can speak loudly.
Okay. All right. So, hello, I'm Sujin Chong, Chief Scientist at ALSEMY. ALSEMY is a startup developing AI-based device modeling software since 2019. And today, I'd like to introduce you to knowledge-based neural compact modeling, which we believe can bring us one step closer to autonomous technology development of the semiconductor industry. So let me get my pointer out. So I'll start with why we think AI-based modeling is needed, followed by a brief introduction to what an AI-based neural network model is, for those of you who are familiar with the machine learning. Then I'll discuss some of the options that can make the neural network model more accurate and efficient, what we call knowledge-based neural network modeling. Finally, I'll share with you what I believe our AI-based device can achieve, an end-to-end autonomous technology development. So the goal of this talk is to introduce you to a new type of device modeling, the neural compact modeling, and provide an understanding of the basics of how this model works. Also, I'd like to share possible directions to make this model more intelligent, hopefully sparking your interests in this new field of semiconductor modeling. So now let's begin. So here is the IC design flow from system specification to IC fabrication. After system specification, there's architectural design, logic circuit design, physical design, which involves layout, physical verification and sign off, and finally, IC fabrication. So active research has been going on in using AI in logic circuit design for transistor sizing, power modeling, and interface optimization, and physical design for floor planning, placement and route, and parasitic extraction. This enables a dramatic reduction in turnaround time. So let's look at a few examples. So on the left is using AI for transistor sizing. So with a 65 nanometer two-stage amplifier, the transistors are sized, evaluated, and sizing is updated based on circuit performance results. This process is repeated until the desired outcome is reached. Also, knowledge that is gained from this circuit is transferred to a different technology node, say a 130 nanometer node or a 45 nanometer node, and or a different topology, say a three-stage amplifier, so that the knowledge gained from one circuit can be reused in other situations. On the right is using AI for chip floor planning, the famous Google AI accelerator designed using AI that many of you probably heard about. The macros are placed one at a time based on a reward system that calculates the reward based on wire length and congestion. So in under 6 hours, chip floor plans that are superior to or comparable to what humans can design are generated. So despite active research and actual implementation of AI-based methods in circuit and physical design, there's limited research in using AI in device modeling. This is surprising if you think about the benefit that can be gained by automating device model generation. With device dimensional scaling becoming increasingly difficult, we're coming to rely more and more on DTCO, design technology co-optimization, and a fast turnaround time for device modeling is critical for this co-optimization. So let's look at the limitation of the current device model that we're using, the analytical model. Now, I don't think I need to go into too much detail with this being a MOS-AK workshop, but let's just remind ourselves. Coming up with an analytical model from design analysis takes years of work by semiconductor experts, and these models have hundreds of fitting parameters. Until recently, this parameter extraction also took months, but recently, use of AI in parameter extraction has been introduced, for example, by Primarius's SDEP. So parameter extraction time may not be an issue in the near future. So anyways, despite all these long hours of hard work, the accuracy is limited since the model contains only known physics that were modeled by a human. So if we're fitting hundreds of parameters with the data we have, and we still can't capture all the physics behind the device operation, wouldn't it make sense to use a data-based approach, namely a neural network model? So before we go into the details of the neural compact model, I'll quickly go through the basics of a neural network for those of you who are not familiar with it. So a neural network consists of an input layer, hidden layers, and an output layer. So there are nodes in each layer that are connected to other nodes. So each node has a weight vector, a bias, and an activation function. So if you focus on one node, highlighted in red here, for example, a linear combination of the inputs is calculated with a weight and bias, denoted as Z here. And Z is inserted into an activation function, a nonlinear function, which can be chosen among different options. So some of the examples are shown here on the right. This activation function is what adds nonlinearity to the system. The output of this function is the output of the node. So say you have m different data with an input vector x and an output y. For each data, forward propagation is done, where each node does the calculation I just described earlier, passing on the output of each node as the input to the next node. So in the end, we have the calculated output y hat for each input vector. Now, this output is compared to the known output value we have, y. The loss function quantifies the accuracy of the calculated output. This is done for n number of data that we have, and the total loss is calculated. What is done next is a backward propagation, in which the weight and the bias of each node is updated to minimize the total loss. Here, the learning rate alpha determines how much change is made in each update. So this forward and backward propagation is repeated for all the data that we have until the desired accuracy is reached, at which point we fix the weight and bias. This neural network is capable of expressing any arbitrary function based on user data with proper tuning of what we call hyperparameters. This includes factors such as number of hidden layers, number of nodes at each layer, the choice of activation functions, learning rate, the number of iterations, etc. So now let's look at the example case where the neural network is used to model device behavior. As with the conventional analytical modeling case, we have measured IV data for different combinations of channel width, channel length, and operating temperature. And our goal is to generate a device model that outputs a current value for the input voltages for a device with any width, length, and operating temperature. We use our measured data to train a neural network with the voltages and parameters as the input and currents as the output. This neural network replaces the conventional analytical equation. Instead of the voltages and the parameters being plugged into analytical equations, they're put into the input layer of the neural network. And we get current as the output, as with analytical equations. This allows us to do data regression, make a neural network that fits the known data points. But is this enough to make a useful device model? And our answer is no. So let's look into knowledge-based neural network models and see how we can improve the models from merely doing data regression. The simple data regression can violate the laws of physics in regions where there is no known data. To prevent this, we can train with inductive bias using domain knowledge-based constraints or using a physics-based neural network. Also, sometimes we might not have sufficient data to produce an accurate model. In such cases, multitask learning or meta-learning can be used to build prior knowledge from other tasks. So let's look at each of the options one by one. The concept of imposing domain knowledge-based constraints is to reduce the degree of freedom in a model by incorporating human knowledge. So if you look at the figures, the black dots are the measured data, and the blue line is the true function. If you allow too little degree of freedom, you would get underfitting, as with the figure on the left. Now, you might think that the more degree of freedom you have for your model, the more accurate you can make it. But with noise, this is not the case, as you can see from the figure on the right. The model is overfitting the data. So by putting a constraint on the degree of freedom based on the knowledge we have of the domain, we can get a good fit. This is usually done by adding a term in the total loss function that we minimize during parameter optimization, so that the model doesn't just follow the exact data, which will result in overfitting. This is called regularization. So going back to our device example, here I'm showing drain current versus drain bias curves. The blue dotted line is the measured data, and the red solid line is from the neural network model that was generated without domain knowledge-based constraints. There are regions where current decreases with increasing drain voltage, whereas the curve should be monotonically increasing. And there are regions where the curve is squiggly, whereas the curve should be smooth. So using the knowledge of the required monotonicity, that current should increase with increasing voltage, and smoothness, that current should increase smoothly with increasing voltage, we can add additional terms in the total cost function that increases when these conditions are not met, constraining the model to follow these conditions. Physics-based neural network is similar in that we use the domain knowledge, but here we're not merely putting constraints. We're modifying the neural network training scheme or architecture. An example is shown here for a physical system where the loss function is calculated not based on the output value, but based on whether the output value satisfies the governing partial differential equation, the boundary condition, and the initial condition. So here are a few examples of applying this to device modeling. One example is the case of modeling charge. So when modeling charge, it is difficult to directly measure charge and provide it to the neural network during training. Making use of the knowledge that although charge is needed for simulations, capacitance is what really matters. Capacitance is used as the value for comparison in the loss function instead of charge. The figure shows how the ring oscillator simulation results, comparing the case when both Q and C were used, AN and 1, versus when only capacitance was used, AN and 2. You can see that the difference is not significant. Another example is to choose activation functions considering the known IV behavior. With the knowledge that current equals to 0 when the drain voltage is 0, the hyperbolic tangent function, which is 0 when the input is 0, is used for nodes connected to the drain voltage input branches, as you can see here. And with the knowledge that current does not equal to 0 when the gate voltage is 0, the sigmoid function, which is not 0 when the input is 0, is used for nodes connected to the gate voltage input branches, shown here. Now, let's move on to the case when we have limited data for our task of interest, but we have more data for other similar tasks. Multitask learning is learning generalized representation for multitasks by training them simultaneously. As a result, we have shared layers, which represent shared, more general properties, and task-specific layers, which are different for each task. So in our device modeling example, the different tasks could be different technology nodes. We might have lots of data from past technology nodes, but limited data on the new technology node under development, technology A in this case. So in this case strain training, we can add the data from other technology nodes, technologies B and C, to data from the technology node of interest, technology A, to better learn the general device properties that is independent of specific technologies. The properties specific to the technology of interest will be reflected in the task-specific layer of that technology. Now, meta-learning is another method that can be used when data is scarce. In meta-learning, we extract prior knowledge by learning to learn from training with numerous related tasks. So the figure on the left shows the difference between multitask learning and meta-learning. While in multitask learning, you learn multiple tasks together so that you can perform those tasks with precision. In meta-learning, you learn how to learn from multiple tasks so that you can quickly learn a new task. So here, by learning to stand, walk, ride a horse, bike, you learn how to learn new sports. And when you want to skate, you can learn to skate more easily. So how is this done? So the meta-learning algorithms are composed of two parts, base learning and meta-learning. During base learning, individual tasks are optimized. Then during meta-learning, the shared parameter of the individual tasks are updated to improve the overall or generalization performance. When we have a new task, the shared parameter is used to help quickly learn the new task. So going back to the device example, We can learn how to learn from data with other technology nodes, technologies B, C, and D, etc. And we can even make use of TCAT data. After multiple learning episodes, when we need to make a model with limited data for a new technology, technology A here, the neural network can quickly learn the new technology. So I've shared with you multiple approaches to make a neural compact model that can achieve high accuracy even with limited data. So before closing, I'd like to share with you our vision, the future we see when we have a quick and accurate AI-based modeling capability. The focus of the conventional EDA market has been in IC design. The use of AI in this area is bringing revolutionary improvements to the IC design process, dramatically speeding up the design process. This is great. However, currently, there can be a bottleneck when a new technology is developed. When a new technology is developed, we need to generate a device model for that technology. And if that takes a long time, this would limit how much faster we can make the process from technology development into circuit evaluation. By automating the device modeling process with AI-based methods, we foresee a future where a full automation is achieved from device design to chip design, creating a new paradigm in the global semiconductor industry. Thank you for your attention.
Okay, thanks, presenters. Does anyone have questions for this presentation? Okay, I have the questions. What are the future challenges of the N model? Can you hear me?
Hello?
What are the future challenges of the N model? Can you explain? What do you think?
Of
the
this
future
neural network
challenge?
model?
Yeah.
Well, actually, we have current challenges, right? So currently, the technology is at a level where data regression is mostly done. And all these new technologies that I just described, these need to be tried. More research is needed. And we need to find out which of these really work with device modeling. Does that answer your question?
Okay, thanks. Does anyone?
Actually, I also would like to add that putting this neural network into circuit simulation is also something that needs a lot of work. So we need to make sure that the model is stable, so it doesn't have any issues of, convergence issues. And also, there's room for improvement in simulations because currently we use analytical models in the circuit simulation. And if we put in neural networks, there could be ways of optimizing the circuit simulation to better fit this model. So this is another field of research that needs to be done.
Okay, thanks. Does anyone have questions?
Yes, may I ask a question?
Yes.
May I? Yeah. Okay. Thank you for your presentation. And could I know how many neurons are there in your AN model?
I don't know if I should be giving out exact numbers, but I'll just say less than 100 per layer.
Less than 100 per layer. That means the total number should be around perhaps a few hundreds.
Few hundreds, yes. Yes.
Okay. So this is for the drain current model or for the capacitance model?
So we are currently focusing on the drain currents model. We also have tried charge models.
Okay,
And so we need to do both to do SPICE simulation.
Okay. Thank you very much.
Okay, thanks again for the printer. Let's get the next speech. Okay. Let's take a rest for 10 minutes.